Hi guys. I'm just gonna get my cameras ready here. How you guys doing this morning? Bright and early. So I have the chat window open. If you want to write things in the chat window, that's totally cool. I'm also trying to admit people into the class. So give me just a second to get everybody here. And then we'll talk. Also, I wanted to let you guys know too, you probably saw it already on my announcement, but all of the lectures are going to be recorded. They record automatically, okay? So if you don't feel comfortable with the recording, you can mute your video, you can mute your audio, that's fine. I'll post a, I'm going to post the lecture videos, you know, as soon as I get them, like by the end of the day, I'll post them up onto our classroom page so that you guys can have those. But just so you know that everything's going to be recorded. But the office hours that we have in the afternoon, that's not recorded. So don't worry about that. If you guys have questions during the class, you're free to like stop me and ask questions. You can also write things in the chat. I have it up on the window, but you know, like I may not see it right away. So you can always like just ask me. You should think of this as like a normal class. Okay, let's see. So let's, I think we'll go ahead and try to get started with some stuff. So I've got the syllabus up here. Let's see if I can make sure all of this is in focus. Okay, I think that's all right. We'll see. This is Math 1342, Calculus 2 for Science and Engineering majors. I just wanted to point out some of this stuff, a lot of it actually I put up in the announcement that I sent you guys last week, but let's just make sure that we're all on the same page about some of this stuff here, okay? Our class, right, is from 9:15 to 10:20. I know our Zoom window says it starts at 9 o'clock, and that's only because Zoom won't let me start the class at 9:15. I don't know why, but so I have to start the Zoom class at 9 o'clock. But we're going to start it at 9:15 and we're going to end at 10:20, even though Zoom says we're going to end at 10:30 because I can't do like scheduling right down to the minute for whatever reason. All right, so so that's our class time. Our office hours, right? I posted for you guys a link in the announcements. It's also on the homepage for the class. The homepage for the class and on the syllabus for the class, I've got a link for the office hours. Again, there's like a date weirdness where I can only do like certain like a month and a half's worth of like Zoom meetings, and then I have to start another link. So like up until I think like the beginning of March or something like that, where there's like the first set of links you're going to use for the office hours. And then after that, there's like another set. Anyway, that's all listed on the homepage and on the syllabus for our class. You guys should be able to see that. I also typically post things. I'm going to post things onto my YouTube page. I'll post the lecture videos there. The turnaround time for that may be a little bit slower than our Canvas page. Like Canvas, I'll add our lecture videos like every day. The YouTube may have like a lag on that, but it'll be there in case like you can't access Canvas for some reason. It's right there. So what you'll want to do is you'll want to look for the playlist for our class, which is Calculus 2. Now, Calculus 2, I've got Calculus 2 lectures and Calculus 2 examples, right? So the examples are actually example videos that I put up last spring when we first went on lockdown, okay? So you guys are free to take a look at those. They usually pertain to things that are in the second half of the class because that, like I said, it happened after lockdown. But all the lecture stuff I'll put into the Calc 2 lecture playlist so you guys can take a look for those. All right, so there's a textbook. Okay, we're going to be using mostly the second textbook, which is Integral Calculus. At the end of the class, we're going to be using the multivariable textbook for a few I think like one whole chapter. We've got like a handful of chapter sections on that. But you'll need that book if you're taking Calc 3 next semester. Okay. Anyway, the textbook will help you like extra examples. I try to do examples that are from different books. So you can kind of get a broader picture of things, although some of the examples I have are also from our book. But then all of the homework problems come from our textbook. But I post the homework problems separately in PDFs those are also up on our Canvas page. So you guys, you might find the textbook very helpful, you know, to take a look through. There are proofs, there's other like stuff going on in the textbook. All right, so let's just do a quick thing. I want to talk about what you guys can expect. So the homework right? So our homework is due every Thursday, but not tomorrow. Don't worry about it. It's due next week. And it's basically the homework that's due is the stuff that we'll be having a quiz on that day, okay? So just to kind of get you guys, I think some of this stuff is all filled out in our syllabus, but let's just talk about it here so we're all on the same page. So pretty much every Thursday, we'll have a quiz, okay? And the quiz will be based on material that we have covered, say, within that week, okay? So like next week, we'll have a quiz on the material that we're covering today and tomorrow, and most likely Monday. I try to make it so that the quiz is on material that we've had a chance to go over in class, right? So when we talk about stuff today, you'll want to maybe download the homework problems and start just taking a look at them. I know they're not due until next Thursday, but the homework problems are going to help you prepare for the quiz, okay? And plus I'll be collecting those homework next Thursday. So we'll have a quiz every Thursday, and then I'll collect the homework on that Thursday that we're having when we're having the quiz, okay? Homework is typically due, I accept it by midnight, okay? And then you guys can upload it to our Canvas page, okay? It's set up right now as an assignment, so you guys can download and take a look at the homework. You don't have to print it out if you don't want to. You can do it on a separate piece of paper, and then you'll want to upload a PDF or a JPEG to the Canvas assignment so that I can take a look at it. Homework is worth 5% of your grade. That's pretty good. It's like, it's enough to bring you from a B+ to an A-, you know, truly, or an A- to an A. So kind of think about that. The most important thing about the homework, though, is that it's going to really help you understand the material. We will spend time at the beginning of each class talking about homework problems. I'll answer questions. Like, we can't spend a whole lot of time, but we can spend some time talking about homework problems. So if you guys have a chance to take a look at them, we can talk about them, certainly. So I'll be collecting it, but I don't have any problems going over homework problems. So you guys can take, you know, take a try at it and then ask me questions, you know, in the next class period or anything up until we take the quiz, and then we can go over it. I do grade the homeworks, but I grade them based on completion. Okay, so what I'm going to do is I'm going to take your homeworks and I'm going to look through, say we have 10 homework problems, right? And you did 9 of them, right? Then you'll get a 9 out of 10. Okay, and then I'll post the grade. You're free to go back and do that last homework problem and then resubmit it, and I can give you that extra point back so you can get a 10 out of 10. Okay, so I will take homeworks that are resubmitted, right, so that you guys can get all those points back. So if you find that, you know, it was a bad week, you couldn't quite get it done, don't sweat it. You can resubmit it, but, you know, make sure that you hand in something when it's due so that I have something to go on. There are some homework problems that have been assigned that are kind of esoteric, and I'll tell you when we get to them that, like, you can ignore this problem or that problem, and I won't count those against you, right, if you don't do them. But I'll let you know when we get there. All right, so homework, 5% of your grade. Every Thursday, I'll collect whatever that set is. And then quizzes, we have, like I said, we have a quiz every Thursday, okay? And then it'll be on that material that we have actually gone over. So if we've talked about new material that Thursday morning, it won't be on the quiz, okay? And as we get closer to the quiz next Thursday, I'll talk about how things work now that we're remote, and how the quizzes and the tests and stuff are gonna happen being remote. Usually to accommodate, just briefly, but to accommodate like the different time zones that we have, the quizzes and the tests too ultimately will be on a 24-hour availability window. So you'll have, like, you know, for the quizzes, you'll have like 20 or 30 minutes to do them, and then, but it'll be available for 24 hours. So you can start it, you know, Thursday night, you can start it Friday morning. It just has to be submitted before the availability window closes. Otherwise, you'll get a 0 on it. The quizzes, because we have so many of them, and this is really where you're kind of pulling material together, I'm going to drop the 2 lowest quiz grades. Okay. I don't actually drop those 2 lowest quiz scores until the very end of the semester when we have all of the quizzes in. So you won't see that scaling of the dropping of the quizzes until the end. But just to let you know, we do drop the 2 lowest quiz scores. But that also means that there are no makeup quizzes, because that'll just count as a 0 that gets dropped. Okay. So if for some reason you can't take it, you know, the quiz that week because of something's going on, you can't take it, it's just going to count as a 0, and then it'll just be one of those grades that gets dropped. Okay. Let's see, tests, we're going to have 2 tests this semester. And you can see them on our syllabus when where they are. Now the tests will be like whatever material we've covered up to that point, the test covers that. The second test will be from that first test to the second test. That'll be that material, but the final exam will be cumulative for the whole semester, okay? The tests are worth 40% of your grade. I know that's a lot. I have no say over the how much the tests are worth. That was told to me by the department. So the tests are worth 20% each. So just to sum up, the final exam, right, is cumulative, and that'll happen. We'll talk about the schedule for the final exam and then how we get prepared for it and stuff as we get closer to it in April. Final exams worth 30%, and then the tests together are worth 40%, 20% each. This part right here, right, the final exam and the two tests, that part was given to me by the department, so I can't change the percentages on how much those things are worth. All of the sections of Calc 2 have to follow that. So the final is worth 30 and our tests are worth 20% each, okay? Then the rest of it, I can, you know, kind of make up the difference on them. So the quizzes are worth 25 and then the homeworks are worth 5%, okay? Just your grades. Attendance now, you know, the attendance, it's really helpful for you to attend every day because, you know, maybe there are questions that you have during the class. And like this is, you can think of this as, like I said, a real class where you can ask questions, like it's like as though we were in person, right? You can stop me and say, wait, can you go back over that or whatever. But if you can't make it, you know, don't worry too much about it, especially like if you're in a different time zone. Like I said, I'm going to post the lecture videos at, you know, by the end of each day so that you guys can see that. Tutoring, when I find out more about the tutoring, I will let you guys know about that. I'll post something like an announcement. And then certainly when I have information about the course TA, because that TA will have their own office hours, I'll post that as well. So you guys can have other resources to talk to people. You can talk to, we have a course coordinator who's Richard Porter, and then we have the teaching director, Alex Martinovsky. You can ask them for questions about stuff if you feel like we can't resolve things. Cheating, you know, hopefully you guys won't cheat. You know, we're trusting you because this is an online class, and I can always tell if you guys are using things like Wolfram Alpha because they often use like methods that are sometimes they're not quite correct. So be very, very careful about using online resources for things like that. Your best bet is to, you know, talk to me, talk to your peers on the homework assignments, but then for your quizzes and your testing, please do all your own work. Let's see, a couple things. Calculators that are really important. Sorry, let's see, I'll show you my calculator. The calculator I use, it's a little bit old, but I really love it. So Texas Instruments, right? It's scientific, it's a graphing calculator. I can do a lot with it. In theory, the course, and it's always a big discussion at the beginning of each semester, whether we should allow calculators at all. And in some semesters, we haven't allowed calculators because in theory, everything that you do, you should be able to do without a calculator. But we're allowing calculators. So we're going to talk as we go about how you can graph things out to help you visualize what it is you're trying to do. But what that means is a lot of the work that you do on the tests and the quizzes, you have to show all of the nitty-gritty steps on things because we know you have a calculator and we know that the calculator will give you things like the integral, what's the integral value, say for example. So we're going to ask you for intermediate steps. And I'll tell you, as we're working through examples in the class, I'll tell you, you need to show this, you need to show this, you need to show this in order to get full credit on things, okay? So I'm trying to give you information and knowledge and skills that you can take for your other engineering classes and for your future math classes, but also trying to give you knowledge and skills that will help you also pass the final exam because the final exam is cumulative. And it's also the questions for the final are made up by everybody in the class, like all the instructors in the class. Okay, let's see. So last day to add, this is some more information that I just got. So I'm putting this up here, letting you know. I can put this up on our webpage too. Pass fail is February 1st to February 8th is to drop a class without a W. February 11th is for a final exam conflict. If you have that, April 21st is our last day of classes, and then we begin our final exam period. Okay. And apparently we don't have a March break this semester because we started this semester like a week later or a week or two later. So we kind of absorbed our March break in January. So keep that in mind that we don't have a March break. Anyway, you guys can see, you can follow along on our syllabus right here, our last page. This is like all up on our webpage too, but it's helpful just to kind of look at it. This is just our schedule of information that we're going to be covering and chapters, right? So these are our chapter, and these are the homework problems. So these are the ones that I'm going to be posting to you in our homework assignments. Okay, so all those homework assignments that are up online, these are the exact problems. Okay, and these come from our book. I copied and pasted them directly in from our book. Okay, the odd number problems have answers in the back of the book, but not like detailed solutions. So you can check your answers on that. Please try to keep up with the material because a lot of the stuff, it's all like cumulative, right? So you don't want to fall behind. If you feel yourself falling behind, shoot me an email, come to office hours, and we'll work on getting you caught up, okay? Anyway, I think you guys can all take a look at this as we go. Something to note on our Canvas page, right? You'll see I have a modules page on the Canvas page. The modules page is listed by week. Okay, so each week is going to tell you what chapter we're covering, right? And you'll see lecture examples. So the lecture examples you'll want to print out ahead of time. Like this is an example of our lecture examples for today. I'm going to fill this out as we go. Lecture examples are very, very helpful. They come from my lecture notes essentially, and it's just a way of making sure that we're all on the same page about what the examples are. Excuse me, and then I will scan in and then upload, scan in and then upload solutions for this by the end of the day, so you guys can have solutions for the lecture examples, but you should follow along and write them down as we're going. This will give you something to help you study from too. Let's see, so yeah, so every week, every day, actually, I'll be posting things to our modules page, and the modules are organized by week. Okay, I know it seems kind of overwhelming. There's a lot of stuff to take in. But if you take a look at our, especially modules page, you'll be able to see like all the resources that you need in order to keep up with what's happening. Okay, so the homework should be posted. There should be a due date on each of those. Lecture examples, lecture videos get posted up there. That's also where you'll find things like our quizzes too. But let me just reiterate, tomorrow's a Thursday, but there's no quiz and there's no homework due tomorrow. But next Thursday, right? Next Thursday, we're going to have a quiz. We'll have a quiz on chapter 1.1 and most likely 1.3. You know, I don't know, probably either of these things will be on the quiz, but definitely these 3 chapter sections will be on our quiz next Thursday. And these will be the homework assignments that I'm going to be collecting. Okay, so keep that in mind. That'll be next week. I think that's about it. I know I talk fast. There's a lot of information to throw out there. If you find while I'm giving a lecture that you think I'm kind of talking fast and maybe, you know, I'm getting too excited about the material that we're covering, please just either say it in the chat, or you can say it, you know, you can just stop me, say it, you know, unmute yourself and just say, you know, excuse me, Dr. Wilson, can you just slow down or repeat that or whatever, and I'll be happy to. I can't slow down like how many days I'm covering on these topics because the syllabus is given to me by the department, but I can certainly slow down how fast I talk. Okay. All right. I know it's kind of a lot to take in, but it's an interesting class, a lot of really neat topics to cover, and anyway, it should be fun. Anybody have any quick questions about stuff, administrative stuff or whatever that you want to ask before we get right into the calculus part of things? Okay, if you guys don't want to ask questions now or in the chat or whatever, it's totally fine. You guys are free to shoot me an email, and then I'll be happy to answer your question individually. Okay, so let's go ahead and get started. So this is chapter 1.1. Let's make sure that's in focus here. Okay, good. All right, so chapter 1.1, this comes from our book. I'm always going to tell you what chapter section we're in so that you can see it in our textbook if need be. This is called Anti-Differentiation. So some of the stuff today is probably a review. Certainly if you've had Calc 1 before, today's class will be a review of material. And then after this, we're going to start jumping right into possibly new material pieces for you. So bear with me, you know, maybe you've seen this before, maybe you haven't, but we're going to roll through it. So anti-differentiation, let's go ahead and talk about that. So let's first talk about what's our notation. So the notation on that is, right, we think of anti-differentiation as the process of taking an integral, right, of a function. So f of x is our function, d of x tells us a whole bunch of things. We're going to get into what d of x tells us, but in the case of what we're trying to do here, d of x tells us what variable we're taking the integral with respect to. So this right here, we can say that this is the antiderivative of our function f of x with respect to x, our variable x, okay? This f of x is the derivative of some function. The whole goal, we're trying to take one of the goals of our antiderivative, our integral process, is to figure out what is that function that has f of x, small f of x, as its derivative. Okay, so you want to be thinking about this small f of x as a derivative of a function. Okay, so just some other notation stuff too. If I do this, f of x dx, right, and then let's call attention here. So you can see, right, on the end, on the bounds of my integral, there are no bounds. No bounds on my integral. This is called an indefinite integral. And this will give us a general solution. If it's possible for us to take the derivative, we'll get capital F of x and then plus c. We need the constant. If it's an indefinite integral, we're going to need that constant. We're going to get into all this detail in just a minute. Okay, but no bounds, it's an indefinite integral. Okay, if I do an integral, let's say f of x dx, and I've got, let's say I've got numbers, you know, x equals a, x equals b. This is the one that has with bounds. Right, these are our bounds here, a and b. This is what we call a definite integral. Each of these has a purpose and they give us different solutions. We're going to be working with both of these this semester. Okay, so this gives us a definite integral. We would say we're going to get capital F of x, and I'm going to evaluate x from a to b. If that doesn't make sense, don't sweat it. We're going to cover it all in detail this semester. Okay, so this is our specific solution. It also tells us something about what it is we're trying to do. I'm not going to go into a lot of detail about this now, but I just wanted you guys to know indefinite integral without bounds and definite integral with bounds. Okay, all right, so let's break up. We're going to talk about this, the indefinite integral for a little bit. So let's do a definition. And then we'll talk about a fundamental theorem of calculus. So definition, so if I've got this indefinite integral, f of x dx, I'm taking the antiderivative of my small f of x with respect to the variable x. What I'm going to get is capital F of x plus c. Okay, so this is our general solution. We just talked this above, but let's write it down here. And c is a constant. Okay, I need that plus c unless I have something that tells me how I'm going to solve for c. We're going to do examples where we have plus c or not, and being able to solve for it or not. Okay, so remember, if I have indefinite, I have the plus c that I have to take into account. Trust me, when you do like quizzes, tests, and the final exam, if you're doing things with an indefinite integral and you forget the plus c, you will lose points. So please make sure that you remember the plus c at the end here. Okay, so let's talk about our fundamental theorem of calculus. Okay, one of them. Okay, so our fundamental theorem of calculus is going to tell us every continuous function possesses, oops, that's an E, possesses an antiderivative. Right, if it's continuous, I can take the derivative, which means I can go backwards to take the antiderivative. So every continuous function possesses an antiderivative. And it's true, this is going to sound a little redundant here, but this says the primary, bear with me here, the primary step to get the definite integral is to produce an antiderivative. It seems like a redundant definition, doesn't it? The way to do the integral is to take the antiderivative. That's pretty much what we're saying. So the antiderivative and the integral are basically two sides of the same coin, right? The antiderivative is our answer, it's our solution. The process of getting the antiderivative, right, is to take the integral. So we're going to talk about how do we do this? Okay, how do we take the integral of things? Give you guys a chance to finish writing that, and then I'm going to turn the page. I don't know why my camera looks a little bit washed out. I'll work on that a little bit later. Okay. Okay, so some theorems that are going to help us actually do the integral and find the antiderivative. So this is a theorem. THM is my abbreviation for theorem. THM. So we're going to say, I'm just going to write down a little math legalese, and then we'll talk about our actual theorems here. So for all x in an open interval for which the functions are defined. We're not defining what that interval is. We're saying x is our variable. Okay, the functions are going to be defined within some open interval. Okay, so the first thing, and these are some rules that are going to help us actually take the integral to help us find the antiderivative. So we take the integral of 0 times dx. Okay, 0 is a constant, but 0 is like taking the integral of nothing. If I take the integral of nothing, what I really get is c, a constant, right? So this is our constant. If you're not sure about that, remember when we remember this is the derivative, right? And this is the function that gives us this as a derivative. Remember, when I go to take the derivative of a constant, if I take the derivative of the number 3, I get 0, right? So that's what I'm doing here. So 0 is my derivative, right? C is the function, the value that's going to give me 0 as a derivative. Okay, so if I go to integrate 0, I get C, a constant. If I go to integrate 1 times dx, so 1 is the derivative of a function, right? So when I just integrate this, I'm going to get x, and don't forget your plus c because it's an indefinite integral. Okay. Now let's just say I'm going to go like this. I'm going to integrate x to the p dx. And let's define a couple things first. I'm going to say this is going to be true if p does not equal to -1. We're going to talk about that case in just a minute. Okay, and p is some kind of a constant term. Constant number. So this is like x squared, x cubed, x to the 15th, things like that, or x to the 3/2. Okay, so p is some number, but it's not -1. Okay, so what I'm going to do is, this is, you guys may have seen this before, this is called the power rule. Okay, so what happens with the power rule when I go to integrate this is I take my variable x, I increase my exponent by 1, and then I divide by that new number. And don't forget your plus c. Okay, this is our power rule. Okay, I'm operating with the power, okay, my exponent. All right, now let's deal with if p is equal to -1, what happens? Because obviously I can't do, right, if I plug in p equals -1, well, it's okay here in the numerator, -1 plus 1, that's just 0. X to the 0 is 1. But -1 plus 1, 0 in the denominator gives me a divide by 0 error. Okay, so that's why we can't do the power rule when p is equal to -1. So I need an exception for it. So if I want to integrate x to the -1 dx, that's like looking at 1 over x dx. Okay, remember, whenever I have a negative exponent, it basically says this number, this variable needs to be on the other side of the dividing line, right? So it's like a fraction. Right, so x to the -1 is really 1 over x, and how I integrate that means I'm taking the natural log of the absolute value of x, and then don't forget your plus c. Okay, things you must remember, the absolute value, remember, because x isn't defined, right, a natural log isn't defined for values of 0 and less than 0, okay? So I have to say, let's make sure that we're always just in the positive domain here. And then don't forget your plus c, okay? Because this is an indefinite integral, so it's we need a general solution for it. If you guys forget the absolute value, you'll lose points, okay? If you forget the plus c, you'll lose points. So these areas are like low-hanging fruit on your final exam where you're trying to make sure that you keep up all of the points possible, and certainly on your midterm exams, you keep up all of the points. You don't want to lose like points in these tiny little areas when you're doing all the other more complicated math correct. Okay, so just some basic rules. These are theorems, okay, part of our fundamental theorem of calculus. All right, so let's just talk about some common mistakes. I go to take the integral of x to the -1 dx. Some common mistakes that that happen a lot, and I see this a lot too. Okay, so the first common mistake is I'm going to treat p equals -1 as any other number, any other power, right? All right, so let's go ahead. I'm going to go x to the -1 dx. I'm going to go ahead and do it. Let's do the power rule. We're going to do it wrong. Power rule, and I'll write wrong. Power rule. So power rule says I'm going to go x to the -1 plus 1 all over -1 plus 1. And I'm going to be really good. I'm going to remember my plus c, right? So let's talk about it. -1 plus 1 here, that's 0. So this is equal to x to the 0. Well, x to the 0 isn't a problem. That's just 1. This is 0, x to the 0, so that's 1 over 0, right? So we have a divide by 0 problem, okay? So this is the part here. It's the denominator that makes this really egregiously wrong, okay? So we have to be really careful, right, that you don't fall into this trap. And people do this all the time. You're cruising right along really fast on a quiz or a test or whatever, and you forget, okay? But remember, right, if you get into a case like this, go back and then think, oh yeah, that's right, x to the -1. Anything, with my exponent of -1, that's a special case. That's going to be natural log of the absolute value. Okay, so that's common mistake number 1. Common mistake number 2 is, okay, let's see, I'm going to make this, right, so I remember that this is equal to the natural log of the absolute value of x plus c. Okay, which means that, that means that, and I'm going to write this is wrong also. This is a wrong assumption. It means that I can do this, right? I'm going to go the integral of 1 over anything dx equals the natural log of the absolute value of anything. And I'm going to add my plus c. Okay, this is wrong, right? It's when I have this here, every time I take an integral, right, I have to evaluate that function in and of itself, right? I have to take a look at what is this function here and how am I going to integrate that? That's actually why we're here in this class, right? So we're learning in this class a whole bunch of skills that are going to help us do this, right? So we can recognize I've got 1 over something. What is that something? How am I going to evaluate that? We're going to learn in this semester, and especially in chapter 1, we're going to learn a whole bunch of tools, different types of integration techniques, okay, for different criteria. Okay, so today is, fairly basic. We're going to talk about basic integration and basic substitution. And as we progress, tomorrow we're going to learn, next week we're going to learn other techniques. Okay, so this whole semester is all about learning how do we do this, okay, because I can't just take the natural log of anything, right? I got to be able to evaluate what that function is that I'm taking the integral of, and then how do I actually work it through, and what do I need to do? Okay, so don't sweat it if it doesn't make sense, because that's part of what we're going to be learning this semester is how do we do that? Okay, all right, so I'll let you guys finish writing that, and then I've got my lecture examples. I'm going to pull out my lecture examples, and I'm going to start filling out my first lecture example. All right, so lecture example number 1, I've got this function. And now what's interesting, so P of r equals radical r. And I want to know what's the integral of r, and I wasn't very good about writing dr. Radical r dr, and I want to find out what's that integral, right? Oh, and look, I was given an initial condition, right? P of 9 equals -7. Okay, so this is unusual in that we're given actually an initial condition. Okay, a lot of the stuff that we're going to be doing in this class this semester is going to either just give us an indefinite integral, so we have a plus c, or we're doing a definite integral and we're going to get a number. Okay, so right now we have initial conditions that's going to actually help us solve for c. Okay, so let's go ahead and do this. So the first thing I have, right, I've got this integral of radical r dr. So the first thing I like to do when I have a radical, right, whether it's a square root like this one or a cube root or whatever, I like to convert it into an exponent. So remember, exponents for radicals are fractions, right? So this is r raised to the 1/2. Okay, it's 1 over whatever your root is, right? Our square roots are so common, we don't write the 2 anymore. So r to the 1/2, I want to integrate that. So let's go back to our rules that we were talking about, right? So it's not equal to -1. My p is equal to 1/2. That means I can just do the power rule when I do this, right? So I'm going to do power rule. Power rule when I go to integrate this one here. Okay, so when I go integrate this, that means I'm going to say, right, I'm going to go r to the, spell it out, 1/2 plus 1 all over 1/2 plus 1. And then let's not forget our plus c. Okay, so 1/2 plus 1, so this is r to the 3/2 all over 3/2 plus c. So I've got this, you know, we're dividing by a fraction, so I'm just going to bring that fraction up. So this is going to be 2/3 r to the 3/2 plus c. And this is going to be my big P of r. Okay, so now what I want to do is I want to solve for c. So I need to use my initial condition. So this is what we need. This is our antiderivative, our general form. Okay, this is like your first step. You have to show this. Okay. It's not enough just to show, to give some kind of an answer. I have to show this first step here, my antiderivative. So I'm going to use my initial condition now. To solve for c. Okay, so let's go ahead and plug that in. So what I'm going to say is, so p of 9 equals -7. So everywhere I see an r, I'm going to plug in a 9. So let's see, I've got 2/3 9 to the 3/2 plus c, and that's equal to -7. So let's work this through. So I've got -7 equals 2/3. So I'm going to do this in pieces. So 9 to the 1/2, right? That's radical 9. 9 to the 1/2, square root of 9 is equal to 3. 3 cubed is equal to 27. So this is 27 plus c. Okay, so now I can divide this into here, right? So 3 goes into 27. I'm going to get 9 times. So this is 2 times 9. So this is -7 equals 18 plus c. Subtract 18 from both sides. -25. Shouldn't it be equal to the antiderivative here? Yeah, you know, I guess technically you're right. So this actually should be lowercase p if I'm going to be really a stickler about it. I think that was probably a typo. Lowercase p. Right, so this is our this is our derivative of this function here. Okay, so capital P gives us our antiderivative. Yes, you're being very concise about it. That was very good. All right, so let's go ahead and put this all back into our equation with c. So our final solution is 2/3 r to the 3/2, whoops, minus 25 equals P of r. That's a minus. Okay. So we were able to use our initial condition in order to solve for c. I can tell you though, most of the time in this semester, we're not solving for c. We either leave c because it's a generic solution, or we're doing a definite integral and we're getting some kind of a value. But we're at least throwing this out here about how we do solve for c, what we can do for that. Okay. You guys all set with this example here? Can I turn the page? Okay, so another theorem that we want to talk about is called linearity of anti-differentiation. And this is important. We actually have been doing this. We do this kind of automatically without thinking about it, but we need to spell it out that it's actually a theorem. So let's say I've got these constants, A and B. These are constants. These are both not equal to 0. So basically we're looking at, I've got this integral of A times f of x, my function, plus or minus b times g of x, some other function. And I'm going to integrate with respect to my variable x. Okay, so the important thing is that I'm adding or subtracting my two functions, f and g. Okay, and I want to integrate that. So add or subtract, my linearity says what I can do is I can take my dx and my integral and distribute it to each of these terms. This only works with addition and subtraction. Okay, it does not work with multiplication or division. We're going to learn this semester tools for helping us, okay, integrate functions that are being multiplied together, okay, or being divided by one another. Okay, but right now, if it's just add or subtract, I can do linearity. So I'm going to go like this: a f of x dx plus or minus b g of x dx. And I'll also throw in here too that if I have a constant term a, I can just bring that outside of my integral, integrate f of x however I need to, and then multiply it by a when I'm done. Plus or minus, I'll bring b out, g of x. Sometimes it's helpful to do that, sometimes it doesn't matter. Okay, so this is linearity here. Like I said, it only works with addition or subtraction. That's the linearity aspect of it. Okay, my second lecture example, okay, example number 2, okay, from our lecture examples here. We're going to apply linearity. I want to find the antiderivative. I've got 5x cubed minus 7 radical x dx, and I'm going to integrate that whole thing. Okay, look, I'm subtracting, which means I can use my linearity, right? So what I'm going to do is I'm going to go 5x cubed dx minus 7 radical x dx, right? So I distributed my dx and my integral sign to each of those terms because it was just being subtracted. I could do that. So now what I'll do is I'll take out my constant terms, so 5x cubed dx minus 7, and I'll convert this radical x into an exponent just so I can see it. And now I'm going to integrate that. Okay, so when I go to integrate this, right, these are both power rule. That's the rule that I'm going to apply when I go to take the integral of these. So what I'm going to get is 5, right? X, I'm going to go 3 plus 1 all over 3 plus 1. I won't always spell it out in such detail, but I'll do it now. Plus C1 minus 7 times x to the 1/2 plus 1 all over 1/2 plus 1 plus C2. Okay. We're going to talk about that C1 and C2 in just a minute. Okay. This C1 and C2, let's pretend, so I'm going to go C1 plus or minus C2. It's still a constant term. I've got a constant, add or subtract another constant that's still just a constant. So I'm going to replace it by just one C. Okay, I don't need to do individual C's for each little piece. I can just do my linearity, take the antiderivative, and then tack on a C at the end because it's still all just a constant. Okay, so let's combine this, right? So 5 x to the 4th all over 4 minus, so this is 7 x to the 3/2. Remember, this is all over 3/2, but then I'm going to bring that up. So this becomes 7 times 2/3. This becomes 14/3 x to the 3/2. And then here's my plus C for everything. Okay. Power roll. We just did the power roll. You guys good with this? I'm going to turn the page. All right, let's talk about some trig rules. This is also a theorem. Okay, so we've got some trig rules that we need to think about. Okay, so let's talk. So the first one is I want to take the integral of cosines. This is actually trig and exponential. Okay, so cosine of x dx, okay, is going to equal to, right? Remember, this is the derivative of what function? That's the derivative of sine of x. And don't forget your plus c. And as we go along to later, as we're talking about things, I'm going to talk about if this x is being multiplied by a number, cosine of ax, what do we do with that? We're going to talk about that as we proceed. It's going to be a part of a different discussion. Okay, so if you have questions about that, we're going to get to it in a little bit. So that's cosine gives me sine. If I go sine of x dx, you have to ask yourself, this is the derivative of what function? Well, it's going to be minus the cosine, right? Because the cosine, when I take that derivative, I get minus the sine. Minus times minus makes it positive. Okay, that's how you want to be thinking about it. Okay, so integral of sine gives me minus cosine. Integral of cosine gives me positive sine. Okay, it's opposite from the derivatives. Okay, so integral of e to the x dx. E to the x, right, we use exponential functions a lot. E to the x is just going to be e to the x and then plus c. Okay, the e to the x is a really unique function because it is equal to its own derivative, right, which means it's also equal to its own integral. Again, don't worry if this x is being multiplied by something else. We're going to talk about how we handle that as we go. Let's talk about a generic exponential function. Right, e is a special case, right? It's e is our base e, right? It's a special number, a transcendental number. But let's say I have like a is some base, a to the x dx. A is equal to 2 or 5 or 15 or whatever. So I want to integrate this generic one. What am I going to get? I'm going to get a to the x divided by the natural log of a. And then don't forget your plus c. Remember, when I go to take like the derivative, right? If I take the derivative of an exponential function, I repeat the exponential a to the x, and then I multiply by the natural log of the base. So if I have those, that's how it's going to cancel out here. So when I take the integral, I get a to the x divided by the natural log of the base. We're doing that here with e to the x, only we don't see it because the natural log of e is equal to 1. Okay, so we're actually doing that process here. We just don't see it because it's equal to 1. But I'm showing you the generic form because sometimes these questions pop up here and there, and you should know. We typically stick with e, our base e, and we typically stick with basically our logarithm base e, right? Because e to the x natural logs, trig functions, they essentially describe our whole natural world, right? Combinations of these things describe our natural world. So these are the things that we think about, okay? Do you guys have those rules? I'm going to turn the page. Okay. All right, so inverse trig. I'm going to give you the two major ones. Okay, our inverse trig. Remember, inverse trig is like arc sine, arc tangent, but it's also written as sine to the -1. Okay, so let's talk about this. And so the first one we'll talk about is, talk about something on an open interval, -1 to 1. Okay, you may recognize what we're trying to do. So I've got this integral of radical 1 over x squared dx. You're often going to be doing work on things and you're going to get it into this format. I can't just integrate this normally, right? I have to be able to recognize that I'm dealing with an inverse trig function here. This is the derivative of an inverse trig function. The function that it represents is sine -1 of x plus c. I don't care if you write arc sine or sine -1, I understand that they're the same thing. Sine -1 plus c. Now, I'll also give you the general form of it too, because sometimes those things pop up. So this is our general form. It looks like 1 over, instead of 1, my a, it's going to be a squared minus x squared square rooted, where a is some number. It can be 9, it can be 5. I mean, a is, it's in the case we're most often going to see it, where a is equal to 1, but maybe not. Okay, so you should be able to recognize the generic form of it. And it looks like I'm going to get inverse sine of x over a, and then don't forget your plus c. Okay, that's your general form. Okay, the second one, the sign, I'm going to give you the inverse tangent one. These are the ones that come up the most often. This one here is going to look like 1 over 1 plus x squared dx, and that's going to equal to the inverse tangent of x plus c. Okay, let's talk about our general solution for that one too. These are going to be really important, especially when on Monday we're going to talk about integration by partial fractions. And then often things end up in a case like this. You need to be able to recognize that you're dealing with an inverse trig form. All right, so general form on this is 1 over, instead of 1, our a is equal to some number. Okay, a squared plus x squared. And what we're dealing with when we do this is 1 over a inverse tangent of x over a, and then don't forget your plus c. Okay, often you're going to have, okay, often the a will be equal to 1, but you should recognize it in case it's not. Like, how do you handle that? Okay, well, you guys finish writing that down. Example 3 has we're going to start working through that. It's it ends up being an inverse trig function, but it's not clear there's a trick solution for how we need to work it through. So let's go ahead, and I think you may even have a homework problem like this. So we're gonna I'll write down, I'll give you a hint that there's a trick solution on it. Okay, so I'm looking at taking the antiderivative, taking the integral of 7z squared plus 5 all over z squared plus 1 dz. If you guys are writing these out, like this is typed in, but when you're writing out z, make sure you put like a line through it so that I know it's a variable instead of the number. Don't assume I'm going to be able to recognize a z from a 2. All right, so already I can see z squared plus 1 in the denominator. It's making me think, yeah. So somebody asked, why is the 1 over a not present in the inverse sine general form? That's a great question. That's actually part of how the inverse sine is derived from basically the Pythagorean theorem. We go through that in Calc 1. If you want to see how that's actually derived, come see me in office hours and I'll be really happy to step you through the derivation for how that is. But the reason we don't see that out front here is essentially it cancels out. It doesn't come into play. How the inverse trig function is derived from the trig functions themselves is an interesting process, but it's basically based on our unit circle and the Pythagorean theorem, essentially. That's how we get these forms here. But yeah, it's not a typo. And why it's here instead of there is, I can derive both of those for you if you want, but let's do it in office hours because it does take time, and it is, it's something that we covered before. Anyway, so great question. It's not a typo. It's meant to be that way. It's just how sine, inverse sine is derived, but I can show you how that is, but I'll do that offline, okay? All right, so let's talk about this trick solution. So I need to be able to integrate this, right? But I've got this z squared plus 1. I'm already thinking it looks like an inverse trig function. So how am I going to solve that? So what I need to do is I need to be creative. This 7z squared, I'm going to pull that off to the side. So 7z squared. I'm going to think about 7z squared differently. So how am I going to think about 7z squared? I'm going to think about that as 7 times z squared plus 1 minus 7. So all I'm doing is I'm just rewriting 7z squared, right? And so, and think about it, right? If I were to distribute this, what am I going to get? I'm going to get 7z squared plus 7 and then minus 7, right? So these are going to cancel. That's just going to equal to 7z squared. But the whole point about writing it this way is that it's going to allow me to break up my numerator into pieces that I can then work with, okay? So bear with me here as this is our trick. Okay, this is the trick solution that we need to do in order to solve this problem here. Okay, so what I'm going to do is I'm going to substitute this in. So I'm going to take this bit right here, and I'm going to substitute it in for 7z squared into my integral. Okay, so let's go ahead and do that. So I've got the integral of 7z squared plus 1 minus 7. Now don't forget the plus 5 from before. And all of that is over, z squared plus 1. And I'm integrating with respect to z, okay? So now what I'm going to do is I'm going to combine this minus 7 plus 5 So what that's going to do is I'm going to go 7z squared plus 1 minus 7 plus 5 is minus 2 z squared plus 1 dz. Now what I can do is I've got two terms in the numerator. They're being subtracted from one another. I've got one denominator, so I'm going to break this up into two fractions. Okay, so it's going to look like this: the integral of 7 z squared plus 1 all over z squared plus 1 dz minus 2 z squared plus 1 dz. All I did was take my denominator and break up my numerator, okay, into two pieces. This is like I find the common denominator and I bring it together into one fraction. Well, now I'm going backwards, right? And this is going to allow me now to integrate, because watch what I can do. Oh, I've got z squared plus 1, z squared plus 1. I can cancel those things out. So really what I'm looking at is I've got the integral of 7 dz minus integral, I'm going to actually bring the 2 out, 1 over z squared plus 1 dz. This right here, well, we wrote it as 1 plus x squared, but you know, it's an addition, right? So it's the same thing. So this right here is just the power rule. So this becomes 7z minus 2 is just a constant term that I multiply by. This here is my inverse trig form, right, that we just talked about. Look, my inverse trig form. Okay, so I'm going to write this as inverse tangent. Nice one. This is z. And then don't forget your plus c. Okay, but the trig solution is, what do I do here at the beginning? I've got the 7z squared plus 5. I can't integrate the way it is. I can't just, you know, how am I going to handle that? So I need to start thinking about how I'm going to rewrite that. Okay. You guys good with that? Okay. So let's talk about the chain rule and how it applies to antiderivatives. So if I talk about the chain rule, remember the chain rule from when I take the derivative. So the chain rule says I've got a function f and it's composed of another function, f of g of x. And I want to take the derivative of that whole complex, right? F of g of x. How do I do that? Well, I have to take the derivative of the outside function, f of g of x. So f derivative, right, of g of x. But then I have to keep nesting my way down and then take the derivative of the functions on the inside. Okay, so I'm taking my derivatives here. So this is my chain rule. Okay, now when I need to think about this in terms of integration, I'm going to think about this in terms of substitution. So if I can substitute, typically I'm going to substitute my inner function with some dummy variable, u equals g of x. Okay, so now if I do that, I'm going to say f of u is the new function that I'm working with. So when I go to take that derivative, what I'm dealing with is f prime of u times du. That means to take the derivative to get du, I have to say du equals g prime of x dx. Okay, so we're using the idea of the chain rule to talk about substitution. Substitution is our first tool. So like, I guess you can think of our first tools for integration are power rule. Okay, and how am I going to be taking the integral of, you know, a linearity of these functions? Okay, where I've got power in my special cases, right, where I've got the my exponent is equal to -1. That's my natural log. I've got some generic trig functions in the inverse trig and my exponentials. Okay, but now substitution is our first tool in our toolkit besides the power rule. Okay, that's going to allow us to start integrating functions that are slightly more complex. Okay, so let's write down what our integration by substitution theorem is. Okay, but it's based on our chain rule, so keep that in mind. Okay, so our theorem. So this is the theorem integration by substitution. When I do integration by substitution, I typically use a dummy variable. You don't have to, okay? But we're often looking for that substitution, okay, when you're doing this stuff. So let's talk about f and g are differentiable functions. Okay, so let's say, for example, I'm going to integrate. I've got f prime of g of x times g prime of x dx. Okay, if I'm going to use substitution, right, remember when I do the integral, I need to have my derivative needs to be in place, and I have to find the function that corresponds to that derivative. Okay, so this is the form that we're talking about here. Okay, and what this is going to look like is, I'll call it f of g of x plus c is our answer. Okay, so now what we do, we're going to do integration by substitution to actually do this integration. Okay, so what this means is typically we look for the inner function that's on the inside, right? That's doing the what our outer function is composed of. Okay, so I'm going to say my dummy variable u is equal to g of x. You can use whatever variable you want, just don't use x if that's the variable that you're working with. I typically use u. So that means I'm going to say my derivative of u is equal to g prime of x dx. My substitution portion comes in because I'm going to substitute my g of x with u, and I'm going to substitute g prime of x dx with du. Okay, so let's go ahead and write that. So the substitution portion looks like this: f prime of u du. Okay, and then I can go ahead and take that integral, which is capital F of u, and then don't forget your plus c. You're not done. You must substitute back for u. So what I'm going to get ultimately is f, u is equal to g of x, f of g of x plus c as my answer. This is something that we look for, right? That you've actually done your substitution, you found the derivative, you substituted it, you found the antiderivative with respect to u, but then you substituted back. If you leave this portion here as your final answer, right, your f of u plus c, you won't get full credit. I have to warn you right now, on the final exams, you'll lose points on it, which means I have to be consistent in my quiz and my test grading. So I have to take off points along the way too if you forget to substitute back. So I'm warning you ahead of time, make sure you substitute back. This is your answer. If you started everything with respect to x, make sure your final answer is also in terms of x. Okay, we're substituting back. Okay. All right, let's do some examples so we can see. The integral of f prime just f, the prime represents the derivative. Yes, so integral of f prime is, it's sort of a nomenclature issue. You're technically correct that f prime, that's our derivative. And I'm kind of, you're right, technically speaking, that I could call this lowercase f of u plus c, because this is our derivative of lowercase f. Our book tends to use capital F to talk about it in terms of the antiderivative, which I would say my capital F prime would be lowercase f. So you're right, technically speaking, I could have also called this lowercase f. Yeah, either way, it's fine. These are just like how we're trying to write it out. But yes, technically, you're correct about that. Okay, so let's talk example 4. Let's go ahead and start doing these examples here. So we want to calculate the integral of cosine of e to the x plus 7 times e to the x dx. Okay, oh, it seems complicated. Remember, you're learning a set of tools that you can use to help you work through complex integrals. Okay, so now what I'm going to do is I'm going to first start at the most simple. Can I just integrate normally? It's a cosine function with exponent. No, I can't integrate normally. Okay, I can't do linearity, remember, because linearity only takes place for things that are being added or subtracted, and this here is one function, e to the x plus 7 is inside of my cosine. I can't break that up. That's its own block. Okay, so I need to start thinking, probably I'm going to do substitution, but let's talk about why. So my inner function on the inside, I'm going to think about substituting that. So u equals e to the x plus 7. Let's take our derivative, du. The 7 goes away, it's just a constant term. The derivative of e to the x is just e to the x, and I'll write dx. Well, look, I've got an e to the x dx there already, which means I can substitute this function here with u. I can substitute this with du. So now what I'm going to do is I'm going to rewrite this now with my substitution in place. So cosine of u du. And I can just integrate normally as a trig function, which is going to give me sine of u. Don't forget your plus c. I'm not done. I have to substitute back for u. Remember, you did that right here. So, take a look at what you wrote. So then your final answer is going to be sine of e to the x plus 7, and then plus c. Don't forget that plus c. Okay. Substitution. Don't forget to substitute back at the end. Okay. We'll roll through a couple more examples, and then we'll quit. Maybe we'll do one more example, and then we'll quit for the day. We can finish off the other examples at the beginning of class tomorrow before we talk about the next portion of things. Okay, so I'm going to integrate t over 1 plus t squared. I'm thinking, oh, hey, that looks like my inverse trig function, except I've got this t here hanging out at the top. Okay, so I have to think about, I can't just do inverse trig the way it is because I've got that t hanging out. So let's try substitution. So u, what am I going to substitute for? I need to be thinking about the more complex function. Okay, so if I substituted for t and I take the derivative, I'm just going to get 1. So I'm going to take the more complex function, so 1 plus t squared. I take that derivative, 1 goes away because that's a derivative of constant term is 0. Derivative of t squared is 2 times t dt. Okay, so what I have here is just a plain old t times dt. So I'm going to solve for t times dt by dividing by 2. So I'm going to get du over 2 equals t dt. So I'm going to substitute in t dt with du over 2. And I'm going to substitute in 1 plus t squared with u. Notice how I didn't substitute for 1 over 1 plus t squared. I just substituted for the most basic of that function. So let's go ahead and substitute that in. So what this looks like now is I've got 1 over u times du all over 2. Well, that's like 1/2 times du. So I'll bring the 1/2 out. 1 over u du. Oh, you know what? That's our special case, right? U to the minus 1 du, which means I'm dealing with a natural log, right? So this is going to look like 1/2 natural log, absolute value of u plus c. Now I need to substitute back in for u. So I'm going to go 1/2 natural log absolute value. Don't forget the absolute value, 1 plus t squared plus c. Okay. Yeah, sorry, I know. All right, sorry folks, I won't always go late. All right, we'll finish up the rest of the examples at the beginning of class tomorrow, and take a look on our Canvas page later today for the lecture video. I'll post it as soon as I can. Okay, guys, have a great day. Nice meeting you all.
Professor?
Yes, what's up?
I have a question.
Bye.
Thank you.
Thank you.
TDT.
Thank you, Professor.
Bye, take care.
So when you go from so when you have du equals 2t dt and you just divide by 2 and you have the t dt, are you just multiplying that? Are you like separating the 2 and then the t dt cancels and just becomes du over 2?
You're talking about this right here. So I think about it as a substitution. So I think about this as being like, I'm going to go 1 over 1 plus t squared. I don't know if you can see that, 1 plus t squared times t dt. Now t dt, right?
Okay.
I'm going to substitute that whole thing with du over 2. Yeah.
Mm-hmm.
And then I'm going to substitute 1 plus t squared with u. So then it becomes 1 over u. And then see how I've substituted this whole block with du over 2. So I recognize there are different tactics. I've seen different people do different things, like maybe they multiply by 1/2 to cancel out the 2. They multiply 1/2, so there are different ways of thinking about it. I kind of like the elegance of recognizing that I have a t dt. I have a t dt here. So I need to get this to look like what I'm going to substitute, right? So if I recognize I have a t dt, well, what do I need to do to get 2 times t dt to look like just t dt? I'm just going to divide by 2. So that means I have to substitute du over 2 in for this whole block right there. Does that make sense?
Yeah, that makes sense. Thank
Okay.
you.
Yeah.
Have a nice day.
Thanks, you too.